In this chart, we will explain the hybridization of the molecule or the coordination compound. Hybridization means when the two atomic orbitals mix together, then there is formation of new hybrid orbital having the different energy and the different shape. Generally it is called as the hybridization. Here in this serial number first, hybrid orbital, sp hybrid orbital. Sp means when one s and another p orbital, one s orbital and another p orbital, they are mixed together. Then there is formation of the sp hybrid orbital, formation of the new sp hybrid orbital, and that new sp hybrid orbital having the geometry is a linear geometry or the linear geometry, and that compound or the coordination compounds having the coordination number is a 2. For example, see here I will show how the geometry is formed or how the geometry is occurred. This is the geometry of the sp molecule. One of the s orbital, this is the p orbital. They are mixed together and then there is formation of the sp hybrid orbital and the sp orbital, and this is called as the linear geometry, and the bond angle between these two orbitals, s and p orbital, this bond angle is a 180 degree. And the example of this AgNH3 2 positive means here is the in the center is the HAC molecule, then two ammonia molecule, one ammonia molecule is here and the another molecule is here, and in this way there is formation of the sp geometry, and in between sp geometry the bond angle between two orbitals is a 180. Then second geometry, see here the sp2 hybrid orbital of the sp2 geometry. In this sp2 geometry, one s orbital is combined to the 2p atomic orbital. In this hybridization, one s orbital is combined to the 2p atomic orbital. Then there is formation of the new hybrid orbital. This hybrid orbital is called as the sp2 hybrid orbital, and the geometry of the molecule is called as the trigonal planar geometry. And in a trigonal planar geometry, the coordination of the compound is a 3, or the coordination number of the compound is a 3. The coordination number depends, or the coordination number gives the geometry to the molecules, and the example of such molecule is called as the Hgi3 Then I explain here the third geometry. It is called as the trigonal planar geometry. This trigonal planar geometry, or this is the trigonal planar geometry. Here is one of the s orbital, then p orbital and p orbital, and here is the center of the orbital. Then this geometry is occurred, or the bond angle between these two is a 120 bond angle is there. 121 angle, 121 angle, and 121 angle. In this way, or this is called as the trigonal planar geometry. In this one, yes, this is p orbital, this is p orbital, and this is s orbital, sp2, and the bond angle between these two is 120, 120, and 120. And the example of such geometry is Hgi3 negative. The next type of geometry is called as the sp3 geometry. When sp3 geometry is formed, when one s orbital is combined with the 3p atomic orbital, then there is formation of the tetrahedral geometry. In this, the tetrahedral geometry, at times the coordination number of the complex is of 4. And then the example of this such type is NiCl4, ZnNH3 dipositive. In this, when the coordination number is 4 of the complex of the coordination complex, that times there is a possibility of the 2 hybridization, that is sp3 or dsp2 hybridization. If the molecule having the sp3 hybridization, then it acquired geometry is the tetrahedral geometry. I show you the example of the tetrahedral geometry is this is the example of tetrahedral geometry. This is the 3 orbital, 1, 2, 3, and one of the orbital is here above the plane, and these three orbital. In this way, the bond angle between this orbital, or the bond angle between this orbital to this orbital is 109.5 degrees centigrade. This is the example, or this is the structure of the tetrahedral geometry. Same, see here, this is the structure and this is the structure is the same. The bond angle between two orbitals is 109 or 109.5 degrees centigrade. This is the third type of geometry. The next type of geometry is DSP2 geometry. In this DSP2 geometry, or in this DSP2 geometry, one d orbital is over one d orbital, then one s orbital and two p atomic orbital combined together, and this formation of geometry is called as the DSP2 hybridization or DSP2 hybridization. When the molecules got the DSP2 hybridization, then it acquires the square planar geometry. And in a square planar geometry, the quadration number of the complex is 4, and the example of such complex is called as the NiCN4 negative. This geometry, or this Cl4, NiCN4, what is the difference between two, or why we show the different geometry? Because he is a weak field ligand and Cn is a strong field ligand. In this way, strong field ligands pair of the electron, and weak field ligand does not pair the electron in a atomic orbital. Hence, this difference arises. Hence, the NiCl4 shows the tetrahedral geometry and NiCN4 shows the square planar geometry. I will explain with the help of the square planar geometry, with the help of this balloon model. This is the square planar geometry. In this square planar geometry, the four atomic orbital, one is the D, S, P and P. It means there are two P orbital, one D orbital and one S orbital. S, P, D, 2 or DSP2, DSP2. It means there's one of the D orbital, S orbital and two p atomic orbital combined together. Then this formation of the such type of geometry is called as the square planar geometry or the square planar geometry. The bond angle between these two is a 90 degree. This bond angle is 90 degree. This bond angle is total 90 degree. In this way, the next bond, the next geometry is called as the D2sp3 or sp3d2. D2sp3 or sp3d2, when inner d orbital is used for the bonding formation, or when the inner d electrons is used for the bonding formation or hybridization, then there is formation of the D2sp3 hybrid orbital. Then geometry of the complex is octahedral geometry, and that times the quadration number of the complex is 6. The example, such example, FeCN6 tri-negative, COH2 6 di-positive. But in this, there are the when the coordination compounds having the coordination number 6, that times possibility of the two hybridization, that is one is the D2sp3 and other is the sp3d2. The first D2sp3 is called as the inner orbital complexes, and when the complexes acquire the sp3d2 hybridization, then it is called as the outer orbital complexes. These inner orbital complexes and formation of the inner orbital complexes and formation of the outer orbital complexes is depend upon the type of ligand used, because there is the use of the type of ligand. If strong field ligand is used, then possibility to acquire the D2sp3 hybridization. If we use the weak field ligand like H2O, then it is possible to use the sp3d2. It is called as the outer orbital geometry. This is the general concept of hybridization and explanation of all these. And I explain here the geometry of octahedral geometry. In this octahedral geometry, four molecules are on the plane 1, 2, 3, 4, and two molecules. One of the molecule is above the plane and another molecule is below the plane. This geometry is called as the octahedral geometry or octahedral geometry. In this way, for example, FeCN6. Please see this example, FeCN6. The Fe atom is present inside here, or Fe atom is present here. One of the Cn atom is above the plane, second Cn atom is below the plane, and fourth Cn CN atom 1, 2, 3 and 4. 4 CN atom is present on the plane. 4 atoms present on the plane, one other above the plane and one of the below the plane. This type of geometry is called as the octahedral geometry. This is the real shape of the octahedral geometry. And the example of FeCN6 trinegative COH26 positive complexes. In this way, we will complete here the concept of hybridization or valence bond theory. After that, we will discuss the next topic, how the geometry of the complexes is formed, or how the geometry of the complex is formed. In examination or in semester examination, semester 3, the question may be asked, explain the formation of complexes or explain the formation of the complexes. I take one example here, or directly question, explain the formation of FeCN6 trinegative complex. This type of question is asked in a semester factorial exam or semester or 5th semester examination. How to write the answer of that question, because this question is asked for the 4 marks. So please see carefully. First of all, write the answer. In answer, write, in this complex, the central metal atom of this complex is a ferrous. Central metal atom of this complex is a ferrous. Then write, coordination number of this complex is a 6. Coordination number of the complex is a 6. 6 CN ligand or 6 silent ligand is attached to the ferrous atom. 6 CN or 6 silent ligand is attached to the CN. Then write down, oxidation state of central metal atom is a +3. Oxidation state of the central metal atom is a +3. Then atomic number of Fe. Atomic number of Fe or atomic number of the ferrous. What is the atomic number of the ferrous? 26. Then write down 26 atomic number. Then in this answer, write down the ground state electronic configuration of the ferrous. Ground state electronic configuration or electronic configuration of the Fe is equal to Ar. How many valence electron of the ferrous? 28. Then 3d6, 4s2 is the hybridization or ground state electronic configuration of the ferrous. But in excited state or in oxidized state, Fe diapositive shows electronic configuration Ar. Oxidation state of the central metal atom is a +3. It means that it loses the 3 electrons. When it loses the 3 electrons, these 2 electrons, outermost 4s electrons is 2, and one of the electron is lost from the 3d orbital. Hence, electronic configuration is the 3d5. Electronic configuration is the 3d5. Then I write in a box diagram. This here 3, 4, 1, 2, 3, 4, 5. This is called as the 3d orbital. Then 4s and then 4p. See here, in a ground state electronic configuration of Fe. In a ground state, total number of electrons in a d orbital is a 6. This I write here 1, 2, 3, 4, 5 and 6. Then in 4s electrons, 2 electrons is accommodated in 4s orbital. Then 4p orbital is vacant. Then in excited state, excited state, electronic configuration of Fe dipositive. In excited state, electronic configuration of Fe dipositive is 3 electron is lost, then 1, 2, 3, 4, 1, 2, 3, 4, 5. 3 electron is lost. This electron is lost, and one of the electron is lost from the 3d orbital. Then 1, 2, 3, 4, 5. Only 5 electron is remaining in a d orbital. Then 4s orbital is a vacant, and then last is the 4p orbital is also vacant. In a hybridization state, Fe, Cn, 6 tri-negative complexes, the Fe 1, 2, 3, 4, 5. When Cn molecule is come close towards the Fe for the bonding formation, and Cn is a strong free ligand, hence it force of the electron, and electrons get paired up in a d orbital. Then these 5 electrons is paired up in a 3 orbital only, 1, 2, 3, 4, and 5. And here see here 2 vacant orbital is available for the bonding formation. In d orbital, then next orbital is a s orbital, and next 3 orbital is a p orbital or 3p orbital. Then Cn gives the lone pair of electron in a vacant orbital. The total number of Cn is a 6 Cn. Then 6 Cn donate the lone pair of electron. Cn, 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 and this Cn. 6 Cn donate the lone pair of electron. I show in a cross sign here. 1 electron pair donated to the central metal atom in this way, donate the electron pair in a vacant orbital, and then hybridization is take place. See here 2d orbital, 1s orbital, and 3p orbital. When combined together, 2d orbital, d2, 1s orbital, s, and p3 orbital. When they are combined two together, then there is formation of the geometries D2sp3 hybridization. And when the molecule acquires the D2sp3 hybridization, it means that it shows the octahedral geometry. To the complexes. In this molecule or in these complexes, only 1 electron is unpaired. Hence, this complex is called as the paramagnetic complexes, and the magnetic moment of the complexes is 1.73 bm. This complex is called as the paramagnetic complexes, and the magnetic moment of this complex is 1.73 bm. This all information, and lastly, write down the structure of these complexes. I show the structure of these octahedral complexes here. This is the structure of octahedral complexes. In this structure, Fe atoms, here is the Fe atoms, then 4 Cn atoms, 1, 2, 3, 4. 4 Cn atoms is present on the plane. One of the Cn atom is present above the plane, and one of the atom is below the plane. In this way, draw the structure. Lastly, the structure of this molecule is like this. One of the atom, this is the central metal atom Fe, then Cn, 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 and Cn. And charge of the complex is tri-negative charge. This is the structure of FeCN6 tri-negative molecule. In this way, we have to explain in an examination. Then you will get the 4 marks or 4 out of 4 marks. See, the next example is explain the formation of COH2O6 tripositive complex. In this COH2O6 tripositive complex, the central metal atom of this complex is a cobalt. Then 6 ligand H2 molecule is attached to the cobalt molecule, and hence the coordination number of the cobalt is 6. Then atomic number of cobalt is 27. Oxidation state of cobalt is +3 or +3. The ground state electronic configuration of the cobalt is argon 3d7 4s2 because 9 electron is present in outermost cell. Then electronic configuration of the cobalt is 3d7 4s2. When 6 ligand or H2 molecules is come close together for the bonding formation, then there is a covalent bond is formed between the cobalt and the H2O molecule. But in excited state electronic configuration of the CO or Sem-Vth atom is argon 3d6 4s0 because the 3 electrons, the oxidation state of the cobalt is 3 and oxidation state means the electrons lost by the cobalt is a 3. Hence this electron is lost in 4s orbital and one of the electrons is lost from the 3d7 orbital. Hence in 3d orbital only 6 electron is remaining. See here in a box diagram, ground state electron configuration of the cobalt is 3d7. This is the 3d7 molecules 1 2 3 4 5 6 7 in a 3d orbital, 4s2 in a 4s2 and 4p orbital is a vacant orbital or the 4p is vacant. In excited state 3 electron is lost from the molecules because the oxidation state is 3, hence he is lost the 3 electrons. Hence from these 2 electrons and one of the electron, these electrons is lost. Then excited state electronic configuration of the CO tripositive molecules or CO tripositive complex 6 2 2 2 means the pairing of electrons take place because H2O is forced to pair up the electron or H2O forced the pair of the electrons. Then pairing of electron is take place here and 2d orbital is vacant for the bonding formation or 2d orbital is vacant and 1s orbital is vacant for the bonding formation because these 3 electrons is minus and this 1 electron is minus from the 3d orbital. This then vacant 2d orbital and 1 orbital is empty here. In the formation of COH26 tripositive complexes, the 6 molecule of H2 molecules donate the lone pair of electrons to the vacant orbital for the bonding formation. Hence, these H2 molecules donate the lone pair of electron, this H2 molecule donate the lone pair of electron, this donate the lone pair of electron, this H2 molecule donate the lone pair of electron, this molecule donate or this molecule donate. 1, 2, 3, 4, 5, 6 H2 molecules because coordination number or the H2 molecules is how many? 6. Hence, 6 molecules donate the 6 electron pair in a vacant orbital for the bonding formation. When see here, when 2d orbital, 1s orbital and 3p orbital undergoing the hybridization and then there is formation of the D2sp3 hybridization. Then there is formation of the D2sp3 hybridization of the molecule. In this molecule or in these complexes, there is no any unpaired electron. There is no any unpaired electron. All the electrons are the pair. Hence, this molecule is called as the diamagnetic nature or the COH26 tripositive complex is a diamagnetic in nature. If the hybridization is D2sp3, then geometry of the molecule is a octahedral in nature or geometry of the molecule is a octahedral in nature. Then what is the structure? Octahedral geometry of the structure. Then see here, this is the structure of the COH26 tripositive molecules. This is octahedral geometry. 4 H2 molecule is on the plane. 1, 2, 3, 4 H2 molecules is on the plane and one is above the plane and another is below the plane. One H2 molecule is above the plane and another molecule is below the plane. This is the complete explanation of the formation of COH26 tripositive complexes. In this way, we can explain the formation of COH26 tripositive complex or any other complexes given in the coordination